Hi, my name is Eric, and this is a presentation on digital color. What exactly is color? Color, it turns out, is a form of electromagnetic radiation which our eyes are sensitive to. Visible light forms only a tiny part of that spectrum. Other electromagnetic radiation includes radio, micro, X, gamma, and UV rays. We can't see these, though, although we have found a use for them. Visible light goes from about 400 nanometers to 750 nanometers and covers a very small part of the entire electromagnetic spectrum. You can see here that I've got a diagram on the electromagnetic spectrum, and a very small part of that, even smaller than what is shown there, is visible light. Even though the visible light makes only a tiny part of the EM spectrum, there are still lots of colors. In fact, there's almost an infinite variety of colors. There are, in fact, billions, trillions, quadrillions, penillions of colors. Our eyes, however, can only detect about 10 million. I've got a diagram here showing analog versus digital capture. Analog for a digital image would be film, and analog for digital capture would be a CD, or it would be a solid state drive, something like that. Film, like a vinyl record, is analog in nature. CDs, hard drives, and solid state media are digital. Analog refers to the ability to record the continuous and precise range and quality of a signal. Digital refers to numbers. Recordings are done by taking a signal and reducing it into a series of digits. Analog media can usually capture the nuances of recording better than digital media can. This is one of the reasons why vinyl records are making a comeback. How is an image saved digitally? Well, they're saved through a series of ones and zeros. We call these zeros and ones a bit. So a 1 or a 0 is a bit. A bit can only hold one of two numbers. By itself, it can't really do anything. As a group together, though, we can start to collect some information. A better way to store information is using a group of 8 bits called a byte. A byte of information can represent any one of 256 numbers. So a bit can only stand for a 0 or 1. A byte can stand for up to 256. And we use the form of a byte for a great deal of what it is we do in photography. Well, how is this stuff stored? Well, it turns out that there are a couple of different ways to store digital media. 1 byte of data codes for 1 pixel on an image. So when you have a picture and you have individual pixels, we'll look at that in a bit. Each of those pixels requires 1 byte. 1,000 pixels needs to have 1,000 bytes. That's also called a kilobyte. 1,000,000 bytes is a megabyte, and it can hold a 1 megapixel grayscale image. That's assuming there's no compression. And 1,000,000,000 bytes is a gigabyte. Well, what is a pixel exactly? So we can see here we have an image, and then from the sleeve of the fellow, we've enlarged that, and then we've enlarged it again, and those little squares are individual pixels. A pixel is a single point of shade or color that is part of an image. A pixel is stored digitally for using information in the form of bytes. A single grayscale pixel takes 1 byte of memory to store it. Now, histograms are a really interesting thing because it allows us to take a look at the spread of pixels in an image. Going from 0 black to 255 white, we have all of the various different shades in a grayscale image here. The number of pixels is vertical, the shade of the pixel is horizontal, and that combination gives us our histogram. Okay, let's just stop for a minute and think about what we've got so far. A digital image is made of small units called pixels. In grayscale, that's no color, a single pixel takes 1 byte of data. A byte is made of 8 bits. Each bit is either a 1 or a 0. There are 256 combinations of bits in a byte. A single byte then can code for any one of 256 different shades. The number 0 is black and 255 is white. Numbers in between those code for various shades of gray. it takes thousands, if not millions, of pixels to produce an image. The larger the image, the more memory it takes up. A 1 megapixel grayscale image takes up 1 megabyte of memory with no compression. We can go from grayscale and we can start talking about color. The difference is that a grayscale image, using the byte as the base storage of data, color requires 3 bytes of memory instead of 1. So you can see on the left there is a grayscale image of the parrot. It takes approximately half a meg of memory. Then there's the color image of the parrot. It takes 1.5 megs of memory, 3 times as much. That's uncompressed. Okay, so you can see on the diagram I've got 3 different shades of blue there, and I have 3 little graphic representations showing RGB, red, green, and blue. Grayscale only uses a single set of numbers, and we say that there is 1 channel of information. Color requires more data to record a single pixel. So in order to do that, we use 3 separate channels, a red one and a green one and a blue one, and together they represent a single color. Each channel still allows 256 levels of that color to be recorded. But when we combine them, we end up with a possibility of over 16,700,000 different colors. Each of those colors has its own channel, and we can represent each channel using a histogram. So each pixel is coded by 3 colors, each one contained in a separate byte. We can produce a histogram for each channel. Notice that we can also produce colors like yellow, and then we have orange and purple and many other colors, and we're producing all of those using only the 3 basic primary colors. So this is where we start talking about bit depth. A monochrome image, you can see in the table there, has 1 channel, and there's only 1 bit per channel, and so the bit depth is 1. A grayscale image, like the one we looked at with the parrot, has also 1 channel, but each channel is made up of 8 bits, which is a byte, and so we say the bit depth is 8. JPEG color, that's what you use when you take a picture with the camera and store it as a JPEG. Each pixel requires 3 individual bytes, 3 bytes altogether, so 1 byte per channel, and there's a total of 8 bits per, so therefore the bit depth is either 8 or, depending upon how you define it, 24. We usually talk about 8-bit color, understanding that there are 3 channels, each one with 8 bits. High color is 3 channels, but each has 16 bits, so that's 16-bit color, and true color is 24 bits altogether. So bit depth refers to the number of bits used in a single channel. It is usually referred to by the number of bits for a single channel, but sometimes we use the multiple ones, as I mentioned. Bitmap is a graphic file which contains black and white information. Grayscales use 8 bits altogether. JPEGs use 8 bits times 3. We usually call it 8-bit color. Digital cameras have RAW files, which gives us greater bit depth. Usually it's a 12 or a 14-bit raw image, and we can convert that to 16 or 24-bit. Here you can see a 1-bit grayscale. This is also called a bitmap. Here we have 8-bit grayscale. Here we have your 8-bit color, and here we have 4-bit color, just as a comparison. And you can see that some of those colors are reproduced in strange ways in the you can see in the pixelated magnification there. Which bit depth is best? For most people, people are quite happy using regular 8-bit color. It uses less information. It gives, because the eye can only pick up 10 million colors and it can produce over 16 million, generally it does a very good job. Sometimes we have different bit depths. We want more to produce something called color banding. Color banding happens when you get transitions between a couple of separate between graduation in a gradual image, and so what happens is that it can cause color banding. If you want to increase bit depth, you can take a look at this image here that I put together. This basically is using Photoshop, and taking a raw image, we can convert to 16 bits per channel. Thanks for watching. I hope you enjoyed this.